Okay, so this is the first video, which is working with splines. If we have a look at the parts that we're going to look at, or I'm going to look at one in particular, this part here is just a flat part, so we can use a spline quite easily on this one. And you'll see that the size of it means it will be bigger than what you see on your screen on the software. So moving over to the software, what we basically do is we have recalled our MCS feature, and we are going to do a spline. So what we need to do first of all is we need to come down with the camera and we need to focus in. Okay, now one thing that you'll see is that if you've got a badly scratched glass, you'll see all the scratching. That will affect it when you're measuring the spline. So what we do is we blind all of that out by increasing the light so that it's not visible. Now, to do the spline, we simply do the spline, close spline tool and the follow closed. What you do is anywhere on this edge you will start it, and it will go all the way around the part and come back again to where it started from. So, as you can see on screen, we now have the full outline of the part. So there's a couple of advantages to this. First one is quite obvious, that if you're working with a part this size, you want to see where you're measuring. Now you can see here we have a little rectangular shape, and this is actually the window here, so you can see how big the part is compared to the window. The advantage is here that if we want to go to this top right hand corner, we just right click and press move here, and the machine will move exactly where you want it to move, and therefore you don't have to mess about with moving left and right and in all the directions to basically get to where you want to go to. And the good thing about this is if you use this after you've done an initial alignment, you can right click and in the playback you can disable it, so it will go a grey colour, but that means that it will remain on screen whenever you're running a program, and it will not need to go around the part again. So if we just re-enable that for a second. Okay, so some of the advantages of using this is that we can use this to measure different things. So if we wanted to measure a line, we can choose a line. If we wanted to measure angles, we can choose the angles. So I'm just going to show you exactly how to do that. So if we want a line to the close spline, what we basically do is we just pick a start and a finish point, and we will have a line. We can then basically take another line from that spline, and we can do a line along the bottom here, and we can say OK to that, and then we can do an intersection point between the two lines. We have a datum, we can then skew that second line, and everything is nicely now in position. This is a good advantage if you've got parts where your datums are on corners outside of where you want to go. So that's using splines. So this is the second video. This is to do with inscribed and circumscribed circles. So if you imagine that you have a piston and a ring that is going onto a piston, you're going to want to know that it's basically going to fit properly. So let's have a look on the machine. What we're going to do is we're going to measure a hole, and we're going to check that hole, and it will give us two different sizes. One will be the size at its smallest, and one will be the size at its largest. So obviously if you have a shaft, you're going to want your shaft, you're going to want to know the largest size of your shaft. If you have a piston ring, then you're going to want to know the smaller size of your piston ring so that they fit together. So let's have a look at the software. So on screen here I have a circle, so I'm just going to measure this circle. I'm going to measure this actually as a closed spline, just following on from last time, so we can actually see what we've got. Okay, and then I'm going to make a circle from this circle here. So you can see that basically what we have is we have a lot of points. Okay, now what I want to do is I want to make a circumscribed circle. So what we're going to do is circle circumscribed to this circle. Now if I increase the magnification here, you will see that all of our points fall within the size of the circle. Okay, and if you look over here, our diameter is 8.076. Now if I do the same but an inscribed circle, what you will now see is that all the points are on the outside of the circle, and we have 7.942. So basically this is telling us that our shaft size and our piston ring size are different. Okay, because if you just do a normal circle, what you will see is that you've got some points that come outside the circle and some points that go inside the circle. Obviously, because this is the circle is never absolutely round, so we use the inscribed and the circumscribed circles to make a certain size so we can check it against the drawing for fits. This is pretty good with ISO fits, especially when you're trying to fit two parts together. Okay, so video number 3. This is looking at measuring cones and spheres. There are many different ways to measure cones and spheres. I'm just going to show you one way that you might find an advantage. You may not. When we have our question and answers later, you might ask about different methods. That's absolutely fine. I'm just going to show you a very good method. Okay, so moving over to the parts. This is our microview sample block, and what we're going to actually do is we're going to look at this cone in here, and we're going to measure it to see what its included angle is. Okay, so over to the software. So let's put our light on. So this here, this is the top face of the cone, and the cone is actually in here. So the first thing I'm going to do is I'm going to take a circle. I'm going to actually use this one so I can get an XY, so I can actually rotate what I need to rotate. So I'm just going to take 2 small radii from the rad tools, or the arc tools as they like to call it, and we have our circle on screen. So I'm going to XY to the circle, so we have a datum in the center of the circle. That helps us when we want to rotate. So while I'm here, what I'm going to do is this face here is what we're going to be looking to measure. Now, as you can see, it's a little bit dark. If we brighten it up, you can see there that we've got very blurry here and in focus here. So what really you want to do is to try and have your focus in the center. So I'm going to focus it in the middle there, because the machine will move up and down to see what we've actually got. Now to do this, I'm going to choose the cone and I'm going to use an area focus. Okay, now the area focus will take many points in the area that we have of interest. So I'm just going to make it about that big. In fact, I'm just going to thin it down a little bit so we got it a little bit thinner. Okay, so we have a number of points here that is taken. These are all focus points. So what I'm going to do is I'm going to right click on that area focus and I'm going to rotate it. So I'm going to rotate it by 45 degrees. So let's put 45 degrees in. And we're going to basically rotate it 7 times because we already have 1, so we need another 7 copies. So once I put OK in there, you'll see that the inputs have now got 8 entries. So if we right click on cone and click remeasure, you'll see that where it starts off here, and then it will naturally rotate around our datum. You can see on the screen up here, this is where we're going to. So that's halfway round. Let's just let it complete its journey. One more. Okay, so you can see here that what we now have is a cone, and there is quite a lot of points on there. You can also see that what we have is a few flyer points here. Okay, so what we can do with that then is we can right click and we can set an outlier rejection. Now the outlier rejection helps us to take out these fly points, okay, because this could be where the light is reflected off the actual machining marks. So we at the moment we've got 320 points measuring this cone. We don't need that many. What we really need to do is have the center amount, which is basically the ones that are closest to a 0. So I'm going to put a standard deviation on here, and I'm just going to move this sigma in to here and the other side to here. So you can see here now that we have a form of fit of 13 microns and a pitch of 89.957 degrees. So we are virtually absolutely vertical. If I was to move that in a little bit more, we've now got 6 degrees and 89.9. We've removed 269 points and we have 51 points. Okay, so that really does give us a good measurement. We've still got 51 points, which is a lot more than you would be able to do with a probe in the same amount of time. So if we close that and have a look here at our actual cone itself, you can see that we've got a really good fit of a cone. We've got an included angle of 89.989. I probably think that this is supposed to be 90 degrees, so we're very, very happy with that. So I'm going to move on to a sphere, and we're going to do exactly the same idea with a sphere. What we're actually going to do is, if you can just see in the back there is a small half sphere. We're actually going to measure that, so let's go over to the software. So let's put our light on, and let's just move to the edge of the part so that we can get a focus on it. Okay, so this one again is just slightly bigger than screen, so I will do a circle so we can datum the circle. Okay, so looking from the top, here's our circle. So let's XY to the circle. Now you can put a Z in here if you want to, but just for the purposes of this I'm not going to. Now, as with the cone, you can do this at 22 magnification, but I prefer on a sphere to actually increase the magnification by quite a bit. So we're going to go down to 121 on mine here. So we're going to try and get some kind of focus. Let's just see if we can go down a little bit, see if we can get it. Let's put the light up. There it is. So this is our sphere here. So we can see where we are on screen at the moment, and we know that our sphere is going to go all the way to the center. So what I'm going to do is I'm just going to move out towards the edge a little bit and come up a little bit and down a little bit so that I've got the focus in the center here. Now what I'm going to do this time is I'm going to do an area focus again, but we're going to do sphere, area focus, and I'm virtually going to cover the center of the screen here, so I'm going to do about that size. And you can see there that the screen moves up and down and gives us quite a few points. Now what you can see here is that we haven't got great coverage, so what we probably need to do is to look at actually adding another row of lights. Now you can see that that's too bright, so let's move that down a little bit and let's try that again. So let's just actually move it up into our focus area so we can get it, see if it goes. We've got coverage more around the center, which is more what I'm looking for. So what I'm going to then do is I'm going to rotate this, and I'm only going to rotate this 90 degrees so it runs a bit quicker, with 3 copies, and I'm going to rerun that. So let's remeasure that a little bit. Okay, so where we have finished, you can see here that we have a sphere, but we have a sphericity of 0.142. So what I'm actually going to do is I'm going to move the camera further in, more towards the centre, and I'm going to focus where we are. Okay, and I'm just going to knock the light back down here because it's a little bit bright. And I'm going to do the same again. I'm going to do an area focus, so we'll just put our more points on. Do an area focus across here. So you can see here we've actually got full coverage, which is really, really good. So I'm then going to right click on here and rotate again, 90 degrees, 3 times. Okay, so let's rerun the whole of the sphere. So you can see that just doing it 90 degrees, we're going to get a lot of coverage here, so your sphere is going to be fairly accurate. So once we go into the centre, we should get a better idea of what we've got. We've got really good coverage there. And you can see in the points fit window here, we've got a lot of points. Okay, so you can see that we're covering most of half of the sphere there. We don't have a great number of outliers to get rid of, so whether you want to or whether you don't is up to you. So let's just have a look at doing that with an outlier. So you can see here we've got 656 points and we've got a very, very good peak. But what we're going to do is we're just going to tie that in a little bit. So we're going to come into about there and about there. So you can see now that our sphericity has now gone to 4 microns and our diameter is 10.902. So that there gives us a really good indication of what that sphere is. And that's a sphere. So finally, we're going to look at the advantages of an area focus over a point focus, especially when you're doing things like planes. So let's have a look at the part. What we're going to do is we're just going to measure this bit of the part here, and we're going to imagine that we're going to be doing a plane. Okay. Now if we look at the screen, what you can actually see here is this is the surface of the part. Now there's lots of marks on here, there's also tooling marks going across and everything else. So if you were basically just doing a point focus and you went down to where you would be recommended to go to on the magnification, let's just get it into focus. There's a possibility, let's put it on axial so we can see it in black and white. There's a possibility that you could actually take your point in the correct place on this one, and then on the next part you're measuring, you actually take it within a ridge or a furrow. So what we want to do is try and avoid that. So the way that we can avoid that is actually by using an area focus as a point. So if we delete the focus point here and we use an area focus instead, what we're doing is we're taking out all the furrows and the ridges and everything else, and you can see from here that we have a lot of points for one single point, but it's an average of all of these. Okay. So if we look at our outlier rejection on this, what you can see is this is actually the surface of the part. Okay, so what we're actually looking for is this top bit. Yeah. Now you can do this manually or you can do it in different ways. So really speaking, we want to get one there, and basically we want to be somewhere in the middle. So probably about there would do us absolutely fine. So now what we're doing is we've got this set of points here, and you can see here that we've just got a measurement. So if we remember that measurement of 9.614, and we go back to doing our other point, so we'll do another point on top of that. We're now looking at a difference only there of 3 microns, but if we try and find somewhere else, another micron difference. So if you're chasing tight tolerances, there's a higher one. Look at 9.621. This could be quite important, especially when you've got surfaces that have tooling marks. now got a 9.607, so between those we've gone 14, 15, 16 microns. So it is actually up to you which way that you want to actually do it. There's advantages in both ways, but if you don't have smooth surfaces and you're doing a plane, I would preferably do an area focus in 4 different places to take a plane. I think that basically sums up what we've actually done today.